In previous work with derivatives, we considered straight line motion, and we looked at the relationship between position, velocity, and acceleration. And namely, we saw that given some position function, s of t, its derivative is the velocity function, and its second derivative, which was the first derivative of the velocity function, was the acceleration function. And so now that we can integrate, we can move in the opposite direction, right? Or we can look at how the velocity function is equal to the integral of the acceleration function and plus some constant. Right? So we're just going to work in the opposite direction. So given that the acceleration function is equal to 4t minus 6 and that v of 0 equals 3, let's find the velocity function. Well, if we integrate 4t minus 6 with respect to t, we will get 2t squared minus 6t plus c. And so this is our velocity function. But one thing that's true is that when t is 0, the whole thing should equal 3. So if t is 0, 2 times 0 squared minus 6 times 0 plus c, the whole thing should equal 3, which means we know the constant of integration is 3. So our specific velocity function in this case is 2t squared minus 6t plus 3. Right, let's look at another example that's similar to this. If the acceleration function is sine of t plus 2t, and we know that v of 0 is 5, let's find the velocity function. Well, if we integrate sine of t plus 2t dt, we know that the integral of the sine of t is negative cosine t. We know that the integral of 2t is t squared plus c. And we know that when t has the value of 0, plus 0 squared, then the whole thing should equal 5. Well, I know that the cosine of 0 is 1, so negative 1 plus c should equal 5, which means that c equals 6. So, in this case, my velocity function must be t squared minus the cosine of t plus 6 to make my initial condition happen. Next, we're going to define two terms. Our terms are distance and displacement. Distance is how far you travel between a starting time and a stopping time, right? Or total distance is another way to consider this, right? How far did I go from the time I started moving to the time I stopped moving? Then there's displacement. And displacement is also a net change. It's what is the difference in distance from where I started to where I stopped. Let's illustrate this, the differences. So let's say I start at this point and travel 80 miles in this direction, and then I turn around and go another 60 miles in this direction to finish here. So I went 80 in this direction, turned around, and went 60 in this direction. The distance I traveled, or my total change, was 140 miles in this case. But my displacement from start to finish was only 20 miles. The difference in distance from where I started to where I stopped. Now, there is a time when the displacement and the distances are equal. And the displacements and distance would be equal if a velocity function is always positive, if I'm always traveling in the same direction. But if a velocity function is not always positive, or I'm moving in one direction and then at some point go back into the opposite direction, then the distance and the displacement will be different. And we'll need to think through both of these situations. Right? We'll need to know, when did that change in direction happen? Now, another thing about distance and displacement in terms of an integral. Distance is an integral from a starting time A to a stopping time B, and it's what you get when you integrate the absolute value of a velocity function. That's how you can calculate distance. Displacement is from a starting time to a stopping time if you integrate just the velocity function, right? Because we'll end up subtracting out some things. So let's consider these ideas with an example. There's a particle, and a lot of the problems on the AP exam involve particle motion. So there's some particle moving along a straight line, and its velocity is given by t squared minus 7t plus 10. And the units on this happen to be, we're told, feet per second. So that's the velocity. The question is, find the displacement and the distance traveled on the time interval from 1 to 7. So we want to find the displacement, and we'd like to find the distance. Let's find the displacement first. To find the displacement, all we need to do is look at the integral from 1 to 7 of our function. We'll just write in v of t because we already know what it is. When we integrate v of t, we get the function 1/3 t cubed minus 7/2 t squared plus 10t, and we need to evaluate it from 1 to 7. Well, first I'll substitute in 7. So let's see, 7 cubed is 343, and 3 doesn't go into that evenly, so I'll leave that like that. 7 squared is 49, times another 7 is 343, so now I've got minus 343 over 2 plus 70, and that, subtracted from that, will be the quantity I get when I substitute in 1, so that'll be 1/3 minus 7/2 plus 10. When I simplify all of this down, I find that my displacement is 6. And my units on this have to be feet, 6 feet, since my velocity was in feet per second. So my total displacement in this case is 6 feet. Now we've got to figure out the distance traveled. Well, for the distance traveled, I need to know something about my velocity. When is my velocity 0, and when does it change directions? So t squared minus 7t plus 10 equals 0. I could use the quadratic formula, but I'll just factor this into t minus 5 times t minus 2. So I know that my velocity is 0 at 2 and 5. And if I test some values before this, if I test the number 1, I'll have negative 4 times negative 1, which will be a positive number. If I test the number, 3, then I'll have negative 2 times 1, which is a negative number. If I test the number 6, I'll have 1 times 4, which is a positive number. So my integral is really broken up into 3 sections for my total distance. I should have given myself a little more space here, so let me clear this out a little bit. So I've given myself some room up here, and I'll look at the integral from 0 to 2 of my function, which was t squared minus 7t plus 10 dt. Now I need to subtract my integral from 2 to 5 of the exact same thing, t squared minus 7t plus 10. And finally, I need to add dt, the integral from 5 to 7 of the exact same thing. Let me explain why that is. So I've got a positive distance traveled on the interval 0 to 2 and 5 to 7, and I've changed direction. I'm going the opposite direction between 2 and 5, so that's going to give me a distance that give me a numeric value that's negative, and the negative just has to do with the distance is traveled in the opposite direction. So if I subtract that portion, then I'm in essence I'm subtracting a negative distance, a negative quantity. And again, the negative has to do with the direction traveled. It doesn't really make sense to say it's a negative distance. Now when I integrate these, we already know what it's going to be. So it's, in all cases, we'll have, I'll write it out quickly. It'll be the same integral that we got in previous work, but now we just need to evaluate all three of these things on their respective intervals. So let's do that. I'll substitute in 2 and 0, and then I'll substitute in 2 and 5, and finally I'll substitute in 5 and 7. And I can see I made a mistake. I should have been integrating from 1 to 2 and not 0 to 2, so I'll fix that first. There, that's fixed. Now I'll substitute in 7 and 5. So now we've got all of these numbers, and once we combine everything to find the total distance traveled, we end up with 15 feet. So you can see that finding the distance is a lot more difficult, and it would have been nice to do that with the calculator as opposed to find the displacement, which is a lot easier because there's less things to keep track of. In the next video, we'll look at a few more examples that are relating this idea of straight line motion with distance and displacement.